Here we're going to investigate exponential functions and their inverses. So let's start off with a function that we should be fairly familiar with. Y equals 2 to the power of x. What kind of function is it? It's an exponential function. How can we tell? It has a variable in the exponent, right? 2 to the power of x. That's why it's an exponential function, because it has that x in the exponent. So what does this function look like when we graph it? Well, luckily, I've got the Desmos right over here already graphed. And we can see it starts off low and it increases very fast. Just to look at some characteristic points, what's the value of the function when x equals 0? Well, 2 to the power of 0 we know is just going to be 1. So that's right there. And then when x is 1, the function is just going to equal 2, which is what we get that point there. And as we keep increasing x, the function is obviously going to continue to increase. If, on the other hand, we go less than 1, or 0, sorry. So, for example, when x is negative 1. When x is negative 1, that's like we have 1 over 2, right? Which gives us a value of a half. And then when we have, for example, x is negative 3, that's going to be 1 over 2 cubed, right? Which is why we get this value, this small value down here. So the function as we go to the left is going to decrease and get closer and closer and closer to 0. Is it ever going to reach 0? Well, think about it. If you plug in a very large negative number, 2 to the power of negative a million, it's just going to be 1 divided by 2 to the power of a million. So it's going to be a very small number, but it's not going to be 0. So we can look at this going to the left as an asymptote. So let's fill out this table on our handout based on that. So here we have a sketch of 2 to the power of x, and we know that's going to look something like that, right? It's going to cross at 1. The domain of this function, can we plug in anything for x? Yep, we can. So the domain of the function is just the domain x is an element of real numbers such that, there is no restriction. It's just x is an element of real numbers. What's the range of this function? Well, where do the y values exist? And just by looking at the graph, you can see that there's sort of that horizontal asymptote at y equals 0. We can't actually ever come up with a number that's negative, right, or equal to 0. Because no matter what we plug into that exponent up here, we're going to always end up with a positive number, right? So y is an element of real numbers such that y has to be greater than 0. We have a y-intercept, and that occurs at, as we looked at with the graph, when x equals 0, y is just going to equal 1. So that's 0, 1. And do we have an x-intercept? And the answer is no, because it's asymptotic to 0, right? So none. And we do have what seems to be a horizontal asymptote when x goes to negative infinity, right? So when x is going this way, we have a horizontal asymptote at y equals 0. Intervals of increase, where's the function increasing? It seems to be increasing here, increasing here, increasing here, increasing here. And it actually looks like it's always increasing. And that is a characteristic of exponential functions. They're always going to be increasing or decreasing. So this exponential function, the interval of increase is just x is an element of real numbers. It's all the numbers. And it has no interval of decrease. So that's our exponential function. And that should be a little bit of review for you. But now the question is this. If I go back up here to this blurb at the top, how can we solve an exponential equation such as this one, 100 equals 2 to the power of x? How can we solve that equation? We might be tempted to maybe try something like this. I'm just going to copy out that equation here. 100 equals 2 to the power of x. We might be tempted to just maybe plug in some values for x and see if it matches. So I would do sort of like a left side, right side deal, right? And I know the left side's got to equal 100, but the right side, maybe I'm going to try to plug in x equals 5, right? So maybe I'm going to try 2 to the power of 5, which that gives me, I think that gives me 32. Okay, so that doesn't work. That's clearly not anywhere near 100. So let's try 2 to the power of 6. This is going to be giving me 64. Okay, that's getting closer. So let's try next one, 2 to the power of 7. That gives me 128. Oh, now we've gone past 100, right? Remember, we're trying to get to 100. So obviously, the number that we're looking for, that x value, is going to be between 6 and 7. So we can continue this. We can try 6.5. If that doesn't work, we can try 6.6, blah, blah, blah. We can basically just use a lot of trial and error to find out what that x value is. So the problem is here, that takes a lot of work. That's not the easiest thing in the world to use that trial and error, and it's also not that accurate. We got to be able to find a more accurate way of finding what x is using some algebra. And the idea is this. It would be handy if we had a function that can undo an exponential. Undo this 2 to the power of x. And functions that undo other functions, we call those inverses, right? So for example, the inverse, just going over here for a second, the inverse of y equals sine x, right? If we're trying to solve for y, it's easy. We just plug in an angle for x, right? And we get it. But if we were trying to solve for x in an equation, we would use, for example, we would use the inverse sign. We would use that x is equal to the sine inverse of y, right? That's how we would solve for x. So same thing here. Can we come up with an inverse of an exponential? And the answer is, yeah, we can. And it's actually called, the inverse of an exponential, the thing that undoes exponentials, is called a logarithm. So if we look over here, I have that written out for you, it's called a logarithm. And the equation of a logarithm, it's pretty straightforward. We just switch the x and the y, right? That's all an inverse is. Essentially, we're switching the x and the y. So if we look at this, what's that going to look like when we graph this function as opposed to this function? Well, think about what you know about inverses and see if you can predict. I'm going to skip over to the decimals in a second to show you what it looks like, but see if you can predict it first. So look at this. Here is our inverse function of 2 to the power of x, 2 to the power of y. And you can tell it's the inverse because it's reflected in that line y equals x. So it's like the reflection in that line. You can see the blue one. So let's look at some of the characteristics of this function here. So we're going to skip back to the table. Look at it first of all, actually. It goes down to infinity here, right? And it looks like it's asymptotic to 0. And then it looks like it continues to increase and increase here. Okay, so let's skip back over to our table and we'll fill it out. Okay, so based on that, our inverse of our exponential or our logarithmic function looks something like this, right? Not exact, but something like that. So the domain of this, it looks like it's asymptotic to 0, right? So this would tell us that the domain has to be greater than 0. So x is an element of real numbers such that x is greater than 0. That makes sense, right? The range, well, in this case, it looks like it goes down to negative infinity here, and it looks like it's just going to keep going forever here. So it's going to go up to positive infinity. So in this case, the range would be y is an element of real numbers. This also makes sense because remember, inverses have opposite ranges and domains, right? So you can see the domain of the inverse and the range of the function are the same, and same thing for the domain of the function and the range of the inverse. Y-intercept, well, it looks like it's asymptotic to the y-axis, in which case there's going to be none. No y-intercept. But the x-intercept, it's just going to be the inverse of that y-intercept, right? Because, first of all, you can look at the graph. You can go back to the graph to see it. But remember, inverses just reverse the points. So 0, 1 is going to become 1, 0 on our inverse, right? So that's our x-intercept. And it does have an asymptote, and that is at x equals 0, as we can also see from our graph. Interval of increase. Again, it looks like it's increasing everywhere, right? It goes up, 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 and continues to go up forever. So this is also going to be x is an element of real numbers, and it never looks like it's decreasing. Oops, not never. None. None. Okay, so that's our exponential and our logarithmic functions. Now, this method right here still doesn't help us with our problem how to solve that exponential equation, right? The exponential equation that we have up here. But it is the first step. The next step is to come up with some sort of notation or a function that can actually do this for us, solve for that variable. And that's where we're going next. So here we go. This is the famous logarithm that you may have heard about. This is how we write that exponential equation in terms of y. So it's basically like this. It's the same thing as this, but it's just written with a y equals. So the log, all the word log means, it means I'm finding the exponent that makes this equation work. So in this equation, we call y the exponent, right? Basically, y is the exponent that's going to make it work. B is the base, so the base of that exponent, and we put that in the log notation. We put that down here. And x is the answer. So x is the thing when you do b to the power of y. That might sound a little bit confusing, and we'll get to some examples which should clarify everything in 1 second. First of all, we should talk about what restrictions log base b of x have. And that's how we say that, by the way, log base b of x. So the way to do this is to go back up to our graph of log x, right? Remember, this is just the graph of log x. It's not explicit, it doesn't look like that, but it means the same thing. So in this graph, the restrictions are pretty clear. X has to be greater than 0, right? We can't do anything here where x is less than 0. So x has to be greater than 0. And there's a good reason for that. Just looking at our function here, we generally look at exponential equations where the base b is positive. If you have a negative base in an exponential equations, you end up getting some really, really wacky stuff. And you can check that out on your own. But it ends up being a non-continuous function, which does all sorts of crazy stuff. So we generally are considering cases where the base is greater than 0. It's a positive base. If the base is positive, are there any numbers here, y, that we can plug into the exponent that are going to give us a negative x value? And the answer is no. No matter what you raise to, or what positive number you raise to an exponent, you're never going to get a negative value. So this makes sense based on the fact that our base always has to be greater than 0. And the graph makes that pretty clear as well. So now let's look at actually how these things work. So I'm asked to change this thing, log base 4 of 64 equals 3. I'm asked to change that into exponential form. Well, zooming back out for a second and looking back at our definition of what a log is, remember, the b down here represents the base of the exponential, and the x represents the answer. The y actually represents the exponent. So if we were to write this out like an exponential, the base would be 4, right? The exponent is the y, or the thing on the other side, 4 to the power of 3, and that equals the thing that's inside the log. In this case is 64. And we know that expression is true. 4 to the power of 3, 4 times 4 is 16, times 4 again is 64. So that equation is true. So see how this is just another way of writing this. That still might seem confusing. The way I actually like to remember how to do this is just zooming in here. I like to remember that it's going to be 4 to the power of 3 gives me 64. And it's sort of like you follow this arrow. 4 to the power of 3 gives me 64. And that is sort of like your hint at how these log functions work. So going to the next question, for example, following that same pattern, it's like I'm saying 5 to the power of 4 gives me 625. So to write this out as an exponential, it would be 5 to the power of 4 gives me 625. Okay? Try the next one yourself. So we have 8 to the power of 0 equals 1, right? Which we know is true. 8 to the power of 0 equals 1. Anything to the power of 0 is equal to 1, except for 0 to the power of 0. So that's how to go one way, how to turn a logarithm into an exponential form. So can we go the other way? Can we take an exponential and turn it into logarithmic form? So let's go down here. So 7 to the power of 2 equals 49. Obviously, that's a true statement, but it's useful if we can turn it into a logarithm, and you'll see why in a bit. So remember, we're going to write log, and then the base of the logarithm, the thing that's the base of the exponential, goes underneath, or sort of like as a subscript. So we would say log base 7 of 49 equals 2. That's what we would say. Remember, the exponent is the thing that goes on the other side, the y value. And the reason why we're doing this is because we want to be explicit in terms of the exponent. We want to find a way to isolate the exponent, essentially, and that's exactly what logs do. So how would we write, following the same pattern, how would we write this next one? Try it yourself. I'll give you 5 seconds to try it yourself. Okay, hopefully you tried it. We have log base 3, that's the base of the exponent, of 243, and then the exponent goes on the other side, equals 5. So again, we would say log base 3 of 243 is equal to 5. And here we go, not much more complicated. It looks complicated because it's got a fraction and a negative exponent, but it's really the same thing. Log base 4 of 1 over 64. I'm just going to put it in brackets so we know, we make sure we're taking the log of the whole thing, is equal to negative 3, right? There we go. So now if we're given a logarithmic equation, or expression I should say, and we want to try to evaluate it, how could we do that? So for example, log base 5 of 25, what does that equal? Well, you can think about it this way. This is going to equal some value. So some value, I'm just going to call this equals x, right? We want to find out what that x value is. Remember what a log is. It's going to be base to the power of x is equal that. So we can rewrite this as exponential form. 5 to the power of x equals 25. So essentially, and then we can look, what's the x value going to be? Well, in this case, it's pretty obvious. Just by inspection, we know x is going to equal 2, right? 5 to the power of 2 is 25. So what that tells us is this whole expression just equals 2. Okay? Moving on to the next one. Log base 3 of 27. What's that going to equal? Well, remember, we want to find 3 to the power of something is going to give us 27. That's what a log does. It finds the exponent that makes that true. So 3 to the power of what is 27? And we know the answer to that should be 3, right? 3 times 3 times 3 gives us 27. But if you wanted to write it out more explicitly, we can make this equal to x, and we can say 3 to the power of x gives us 27. So x has to equal 3, right? So going on to the next question. Log base 2 of a quarter. So 2 to the power of what is going to give us a quarter? This one's maybe a little bit more tricky. So let's write this one out in exponential form as well. 2 to the power of what is going to give us a quarter? 2 to the power of x equals 1/4. A little bit more tricky here. Think about it for a second. Well, remember, we can always put something in the numerator, right? Something that's in the denominator, in the numerator, if we give it a negative exponent. So this is like the equivalent of saying 4 to the negative 1, right? That's another way of saying 1 over 4. And if we put this as 2 to the x, can we now figure out what this is going to be? Well, just by inspection, like 2 squared is going to give us 4, right? So what do we have to do to that exponent to give it, to basically make it equal to 4 to the negative 1? And the answer is 2 to the power of negative 2 will give us 1 over 4, right? Because it's going to put basically that 2 in the denominator and raise it to the power of 2. So whenever we get a fraction like that, we're just looking for basically the thing that goes in the, basically it's going to be a negative exponent that puts it in that denominator. So there are a lot of questions here for the rest of this page. What I want you to do is I want you to try these out yourself. Pause the video here, try D through L all by yourself. See if you can figure them out. When you're done that, unpause and we'll go through each one at a time and discuss them briefly. Starting with D. D is basically saying what power of 1/3. So actually, let me just write this out in exponential form. 1/3 to the power of x is going to give us 27. And I'm going to put that in brackets because both the numerator and the denominator are to the power of x, right? 1/3 is the base. So again, this is another one sort of similar to the previous question where we have a fraction, right? So I can always flip the fraction, or I can bring the thing that's in the denominator up to the top if I make the exponent negative. So could I not go like this? So all I've done is I've brought that 3 up to the top. I've basically took the reciprocal of that fraction by putting that negative x there. So now here you might be able to figure it out just by inspection. But if you're still a little bit confused, one thing that I could do to further simplify this is I could raise both sides of the equation to the power of -1. So think about what I'm doing there. If I raise this side of the equation to the power of -1 and this side of the equation to -1, remember, our laws of exponents say we can multiply these two things, right? So to simplify this, I'm basically just going to get 3 to the power of x equals 27 to the -1, right? Or just, yeah, let's do that, 27 to the -1, right? So the question is, what value for x that I put in there is going to give us this, right? So we know 3 to the power of what is going to give us 27? And the answer is 3. We've done that one before. So 3 to the power of what is going to give us 27 to the -1? And the answer is 3 to the power of -3, right? If I plugged in a -3 here, what that's going to give me is it's going to give me 3 to the power of, well, it's like doing this. It's like doing 1 over 3 cubed, or 1 over 27, right? Which is the same thing as 27 to the -1, which is 1 over 27. So that tells us that x has to equal -3. Okay? All right, moving on to the next question. Log base 12 of 1. So turning this into exponential form again, 12 to the power of x gives us 1. So 12 to the power of what gives us 1? And the answer might not be obvious at first, but think about it. What exponent always gives us 1? And the answer is 0. Anything to the power of 0 is equal to 1, except for 0 to the power of 0. But anything else to the power of 0 is 1. So the answer is x has to be 0. And that's actually, if we skip down to the bottom of the page, that's one of our rules down here, a general rule. Remembering these rules can be really helpful to make problems a lot quicker to solve. So the first one here, log base b of 1. So basically it's saying b to the power of what gives us 1. So the answer to this, no matter what the base is 0. Okay, so that's a quick little shortcut that you can remember. Let's go on to the next question now. Log base 17 of 17. Well, this one might look a bit silly, but if we turn it into exponential form, it should be pretty obvious. 17 to the power of what gives us 17? And the answer there should be pretty obvious. X has to be 1, right? 17 to the power of 1 is going to give us 17, right? So the answer is x has to equal 1. This is another one of our rules if we go down to the bottom of the page. If the base and the thing inside the log is the same, then x is just going to equal 1. So we can fill that out all the way down here. Log base b of b is always going to be 1 because b to the power of 1 is always going to give us b. Okay, going on to the next question. This one we know is going to be 2 over 5ths to the power, or 2/5 to the power of x is going to equal 125 over 8. Ooh, that's a bit of a crazy thing there. One thing to notice is 2 to the power of something can give us 8, and 5 to the power of something can give us 125. So we know if we flip this fraction around, it might look more like this. And the way we could do that, obviously, is by taking that, making that x negative. So it's like saying 5 over 2 to the power of -x is going to be 125 over 8. And then we can think about what power of 5 gives us 125, and what power of 2 gives us 8. And the answer to both of those cases is 2 to the power of 3 gives us 8, 5 to the power of 3 gives us 125. So x basically in this case in order to make this work, has to be -3, right? Because -3 is a number I would have to put into this equation in order to make this true. So x has to equal -3, right? So the key is whenever you flip the fraction, whenever you have to flip the fraction, the answer is basically always going to be negative. And then look for the number that gives you the exponent. Here's another one that's a bit of a mess, but before actually doing it, let's simplify it a little bit. So we would say log base 6 of 36, the cube root of 36, another way to write that is 36 to the power of a third, right? So if we write this out in exponential form, it's like we're saying 6 to the power of something gives us 36 to the power of 1/3. And remember, when we're solving for exponential equations, one way to do this is to make the bases the same. So how can I make the bases the same here? Well, 36, remember 36 is just 6 to the power of 2. So if I rewrite this equation as 6 to the power of 2 to the power of 1/3, right? All I've done is I've replaced this 36 with a 6 to the power of 2. Those two things are equivalent. And now it's pretty obvious if I distribute this 2 to this 1/3, I end up getting 6 to the power of 2/3 equals 6 to the x. And then just by inspection, I know that x has to equal 2/3, right? Those exponents have to be the same thing for this whole equation to be true. So essentially, x has to equal 2/3. Okay, so that strategy, remember, is called finding the common base and then using inspection to solve for the variable. So I is actually a little bit easier than the previous questions. It just gets you thinking a little bit about what logs actually are and how they can be used. So remember, log base 3 of 27, really what that is, it's looking for the exponent. 3 to the power of what gives us 27? And the answer to that is obviously 3. So log base 3 of 27 just evaluates to 3. And then log base 5 of 25. Remember, that's just looking for what exponent of 5 gives us 25. And the answer here is 2, right? So these two complicated looking things just simplify to 3 and 2. And then obviously we can just add them. So the answer to this equation is just 5. So here we have an interesting one. 8 to the power of what will give us 8 to the power of 24, right? If we wrote this out in exponential form, it's like saying 8 to the power of x equals 8 to the power of 24, right? This whole thing is the thing that's in the log, so it just looks like that. And when we write it out like that, it's super obvious. What's the answer to this? X has to be 24, right? To make that equation balance. So this looks like a super obvious question. But this is actually a pattern that if we remember this, when the base and the base of the thing inside the logarithm are the same, the exponent is just going to equal the answer, right? Or what that logarithm evaluates to. That's one of our little hints down here. B to the power of what gives us b to the power of x? Well, the obvious answer to this is just x, right? By a definition of a log, b to the power of x has to equal b to the power of x, right? It's pretty obvious when you say it like that. But remembering this can help simplify our calculations. Okay, this one looks complicated, but let's think about what that exponent actually means, right? So it's 5 to the power of some ugly thing, log base 5 of 125. But remember, what does that exponent actually mean? It means 5 to the power of something has to give us 125, right? And what's 5 to the power of what gives us 125? 5 times 5 is 25, times 5 again is 125. So that exponent, even though it looks ugly, it's just equal to 3, right? So 5 to the power of 3 is what this thing simplifies to. And the answer here, when we simplify it even further, is just 125, right? So this is another little pattern that if we remember, because you notice this up here is the same thing here. And remember, the thing to remember is that what a log is, when we evaluate a log, it equals the exponent, right? That's the whole point of logs. Logs evaluate to the exponent. It solves for the exponent. So if we're looking at the exponent here, it makes sense that the exponent would just be the answer to the log, or the thing inside the log, right? So essentially, when we go down here, it's one of our patterns. When we have the base of the exponential, being the same thing, the base of the exponential being the same thing as the base of the log, the answer is just going to be x. That thing is just going to simplify to whatever x is. Because the whole point is that we are finding the exponent that makes that thing true. And now we have the last question of the page. So 3 to the power of what gives us 92? That's essentially what this thing is asking us for, right? 3 to the power of what gives us 92? So you can think about it. You can try something. 3 to the power of 4 gives us 81. That doesn't work. 3 to the power of 5 gives us 243. So there actually is no whole number that we can put in for x to get this answer. So you might be thinking, well, like, yeah, how do we do this? Because this was essentially the whole point of this lesson, right? We want to be able to solve equations like this. And we are going to use log to solve equations like this, but you're going to have to wait for the next lesson to find out why.